Hello everyone. You can see my screen, right? So, yeah, so this week's content primarily covers sequential learning tasks, right? Um, so let's see some. So, what are sequential learning tasks? So, there are so many variants of it which you can see here on the screen, right? One to many, many to one. So, does this mean anything to any of you? Like, what does one to one sequential learning task mean? Yeah, I know it's one input, one output, but an example of that. Like, what is a task which takes in? Okay, forget sequential learning, like the term. Any task that takes in one input gives out one output. Name a task. Speech recognition. But speech is not really one input, right? Like you're talking, there's so many words. Image reconstruction. Okay, fine. Yeah. Image reconstruction, image classification, all that is, yeah, one to one tasks. So, what is a one to many task? Image captioning. Yeah. So, you give an image and you want a description of that, right? Like, which is, so the output consists of multiple elements. Object detection from an image. Yeah, you give an image, you get multiple bounding boxes. Fine. Yeah. What is a many to one task? Like I have a video, I want a summary of that, suppose. So it is a sequence of frames, right, which are like act like inputs, and I want a summary from that video summarization. So it can be like a many to one task. So what is a many to many task? Captioning captioning is a one to one many task, because I'm giving one image and I'm getting out one caption for it. Many to many is, say, language translation. Suppose I want to translate from one language to another. Music generation. How is generation a one to many task? Like music generation meaning, say I want to generate a song of some genre. So like, say the genre is the input and I get a whole song as an output, right? It is not a many to many task. It's more like a one to many. language translation, or translating between modalities like text to speech, speech to text, such tasks where what based on all the previous notes it generated the next note. uh, yeah, in that sense, yeah. Um, yeah, if I give a sequence and I mean like one part of the song and I expect it to complete it, then yeah, it is many to many. So there are two forms, right? One is many to many, and like there are two versions which is. So translation, yeah, this should usually be translation, and if there is a one-to-one mapping, which is also not necessarily there in translation, but yeah, like sequence sentence completion or like music generation, like where you're trying to complete something, right? So when we are writing things, when what we get suggestions, right, of what the next word can be, so all such things come under many to many. So what is a fundamental building block behind all this these kind of tasks? Are these recurrent units, or at least they were once upon a time. So what are recurrent neural networks? So recurrent neural networks meaning like we have a basic building. So there is a fundamental building block, that is a neural network, like say this element, and then that is repeating over and over again, which takes in different inputs with time. So there's a time element as well, right? Unlike CNNs where you have one image and that's it. Here we have the time element as well. So that's why it's called a recurrent neural network. So it has um, so here this x here, this is the input at time step t, and this a, or in some conventions you would have seen ht minus 1 or a. So this which gets passed on, right, like this is the hidden state hidden state of the recurrent neural network, and then this is the output of the recurrent neural network unit. So these could be like different words, right, which I give in English and pass it through an RNN, mm, and I get the output in the other language. So it's a simple function where it you have one matrix that operates over the hidden unit and one matrix that operates weight that operates over your input. So these are the two inputs for the recurrent unit, and then there's a bias term. So this is your hidden state, and then this is the output. So the output takes in your hidden state and gives you the prediction like y. And so the main thing is all these weights, right, like the weights which you operate over the hidden state, input state, and then to get your output, all these are common, that are shared across time or across inputs. So they are not different, so that is why usually it is also represented this way. um, so this is your say input, and then this is your hidden state, and then this is your output, and this gets repeated because there are only three elements, and the network is repeated. So yeah, recurrent neural networks were the first thing that came out to handle sequential tasks, I think. But then obviously there were so many issues with it. Can from whatever you've learned from all your previous classes, can you name what can be a drawback of this recurrent neural network? So suppose I give uh, just one statement, like one statement, and I can get a good translation of it from a model trained for translation. But if I have uh, if I have like a whole one whole page or one whole chapter of a book, and I'm training to translate it over such long sequences, would it still be easy to train, or would there be any issues? Yeah, vanishing gradients. So if the length of the sequence is really long, then I would not be able to backpropagate my gradients. I would not have enough gradient to pass it completely back, and I might not be able to actually update the model sufficiently. So I might not end up learning anything good. So there is this one main issue of vanishing gradient in recurrent neural networks. So how do we, so the previous time when we studied about recurrent, I mean vanishing gradients, what was the fix for it? Even in neural CNNs, we did discuss about it, right? Like if I make the depth of the network really huge, then I might not be able to backpropagate it, which is the exact scenario here, where if the length of the sequence is really long, then I can't backpropagate till my first input and so on, so I might not be learning something new. Identity connections. Yeah, in ResNets we did that identity connections, right? Or like skip connections, so that the gradients get backpropagated. So, can we do something similar to that in recurrent neural networks to mitigate that problem? How do we introduce such skip connections or something? And so in this function, I mean the, so this is the recurrent function here, right? So which of this is would actually be causing the like a cause for not retaining the gradients? It would be this function. Like with this is how it gets backpropagated through time, right? Through this WAA, the hidden layer unit, which I multiply with. So because of this multiplication, I might be losing the gradients. So what I have to do is, if I have to retain the information, then there is somehow I have to preserve this hidden state well enough, so that the information gets propagated in the forward and backward pass well, so that yeah, you can handle long range sequences. So that is done by yeah, LSTM, yes. Yeah, so why does that happen? I mean, the problem with vanishing gradient, the gradients become really small, right? So at some point, your weights might not get updated sufficiently enough if the gradient is really, really low. So the weight will remain at the exact same state and the network will not really learn. So the solution for that is this long short-term memory. So how do they manage to fix this problem of long range dependencies and vanishing gradients? Using gates to control memory, yes. So at every time step, so they have these different gates, right? Like LSTM has four different gates: input gate, forget date, cell state, and output gate. So input gate is like the new word at every time step. Then you say the new word I get. So forget. So cell state is actually the one that is carrying forward your information like this in the forward manner, right? From the previous step, so I get, so here I get mm, something from my previous state, and then I take the new input. Uh, I update my cell state using the new input. So this is like the old info, and then here I get something new, and I combine the old info and new info to get my new current cell state. And so this is my current cell state. So I use this to get some my output also, right? Like this is like my accumulated information at times. This is like accumulated previous and current time step info. So this is my knowledge I have at the current time step. So I use this, and then I use this to predict something out, right? So that is why it goes this output. So yeah, so I the output gate is a function of the cell state. So but then how much of the old information do I retain and how much of the new information should I accommodate? So for that they have this forget gate. So this forget gate, so all these gates here which we have, right, they give out the red gates give out are sigmoid functions. So what is the range of the output of sigmoid function, like min and max value of a sigmoid? 0 and 1, 0 to 1, right? So sigmoid is it's like a soft switch, right? It is like this. So it can be thought of like a soft switch, which gives me a measure of how much if I multiply something with the sigmoid, so it acts like a weight, right? So this forget get retains how much information, I mean, gives a measure of how much of my previous cell state should I retain. To be retained. Then there's this input gate. So this takes in the new information. I pass it through yeah, the sigmoid to get a weight of how much of the new information to incorporate, and the stan function, this function, so this is to process the new information. So I multiply these two, so this is the new input which I want to incorporate into my cell state. So all these the input forget and output gets are all of the form, like you all are of the form they taken, I mean, that are on output of the sigmoid function, which takes in, so there is some weight and which operates over the hidden state, that is previous time steps are what I mean, the hidden state, and then the current time steps input, this plus some bias. So it incorporates the previous information, current information, and then it gives out a decision of how much I need to retain or incorporate like a new information. The cell state at current time step, it is a function of uh, so output of the forget get, like how much the weight it comes out of the forget get into the previous time step, plus how much of the new information do I want to retain. So I get here, right, like this place. So this is the output, the weight for from I get from the input get, and this is like my current cell state. So it's a weighted combination of these two. And then hidden state also, so then the next hidden state also gets updated as a function of my output get. Which happens here in this part. So when will this network LSTM become like an RNN? Suppose you can manually modulate or like force this gate, the sigmoid values which you come out, which comes out of these gates. So what is it that is changing RNN to LSTM? And if I want to undo this RSTM to make it like an behave like an RNN, what is that one thing which I'll have to change here? Can I manipulate these weights of these gates manually so that it mimics an RNN? So there are these three things, right? FT, IT, and OT. Three weights which I'm getting. So what part of this is actually making it like a LSTM to retain the old information? Like which gate is responsible to retain old information here? The forget input or output gate? Input. No, input is this is the current time step, right? Old information is captured in this step, this element CT minus 1. So this gate, the forget gate is, I mean, forget gate is a waiting function, right? That is determining how much of old one I have to keep, old one I have to forget, how much of, yeah, new one, how much of new one to incorporate is this. So if at all I make this forget get, if I make this 0, then it will become very much like an RNN, right? I don't have this connection. this connection anymore. It takes in input, it becomes only this part of the module. So it will reduce to kind of like an RNN, because in RNN what do we have? We take in the input, the hidden state, and we get an output. So all these are anyway a function of the hidden state and input state, like CT tilde. CT tilde. So this is a function of hidden state and input state. And if I make ft 0, then I don't have this fault component. I don't have that skip connection kind of thing. Uh, it kind of reduces to an RNN. So although this is not exactly a skip connection, because we have this weighting factor, right, of how much to retain and how much to not. So it is not like a binary residual, exactly like a residual connection as it was done in ResNets directly, but it becomes like a weighted skip connection. So because I want to incorporate new and old information both, right? Hello. Okay, I hope you can hear me. Sorry about that. Okay. uh, yeah so LSTMs, so they may primarily address the long sequence problems, right, due to vanishing gradients kind of thing. And then there were many variants of LSTMs. One famous variant was this gated recurrent unit. So here they combine this, like like the input and forget gate, and output gate and cell state, to make it as like reset gate and update gate. So this kind, they still have that like this connection which is like which carries forward that information with time. So it will handle the vanishing gradient problem, but it has lesser gates and and lesser weights here, right? So it is um, it's a smaller network. I think it's computationally more lighter, but still predominantly addresses the vanishing gradient problem as well. So there are also these other variants of RNNs, like bidirectional RNNs, right? Which rather than so, but this can be used only if we have in tasks where we have access to the whole information at once. Like if I can have if I have to do sentiment classification on some text, like I give a book and then it has to say what kind of genre it is, or what kind of mood is expressed in a particular statement or something. So I have the whole statement at once, so that I can pass and process all the words together. Only in such cases I can use this bidirectional RNNs, where so this is my input, and then like I have two hidden states, one going in the forward direction, one going in the backward direction. And my both of these the hidden state, like this neural network element, right, that takes in as input your so the forward one will take in as input the hidden state and the current input in go in the forward direction, and the other recurrent network which is like exactly in the opposite direction, that takes in as input one is the input and the hidden state, but the hidden states start from last. So it takes in the last word and yeah, so basically at the same time an input is processing my current state, previous time step in the left direction, and also information in the right direction, right, in both directions I'm accumulating information and processing it to give out my output. So when does this kind of things help, like uh,
Ma'am,
yes.
yes, ma'am. Actually, ma'am, this is the problem solving session for week 7, no?
For which?
For week 7. Ma'am, this is the problem solving session for week 7.
Yeah.
Actually, ma'am, we had some programming assignments, so will you help us on that?
uh, what assignment? I mean, if it's a graded assignment, I'm not supposed to directly help you with it, but like if you
No,
have.
not directly, ma'am, just how the coding and everything. Actually, the assignment is not running. It is giving error because I cannot find the image. Uh, it was asking to load the image, but what image actually? I just can't find the image there in the assignment.
Which week's assignment is this?
And this for week 7 only. If I can get the image, then I can solve it. But I'm not getting the image only.
As in, was the input file not given or something? Actually, we have to upload the image given in the same drive. Okay. Maybe you have to check where exactly your path is that input image, like give it, make it accessible correctly,
So
right?
any image I can upload.
Yeah,
Oh, I can upload any image.
I suppose so. To at least validate what is happening, you can use any image and run, right? Okay, Tushar, like, what was that assignment? Do you know if they've given an input file or the specific image of a dog is provided in the same drive? To validate, you can use any image, but if they're grading it, then maybe you'll have to use the same input. You're sure, Tushar, you're sure that file is accessible of that dog? Okay. Olivia, can you check once again? Okay. Like maybe check now only at some time and see if you can access it. And if you are running it on Google Colab, I think you'll have to mount it and then upload this. Mm, e- Either mount your drive so that you can access this file, or temporarily download and upload this image so that you can run your assignment. Okay, coming back to this, yeah, bidirectional RNNs can be used if you have access to the whole input at once. Uh, on a similar, um, along similar lines of thought, later, I think this is your next week's content. So there are all these transformer models, right, which all of you would have heard, transformer architectures. So this transformer architecture also does something similar where you give the whole input. It can look up what comes ahead, the whole, and process all the text at once. So it's not really sequential as in the sense as RNN is designed. So all the input tokens are accessible, and each token can look and attend towards its neighboring tokens, everything, and then process all of the whole content together. So these transformers, which are based on this attention mechanism, are what are the backbones of pretty much every damn uh, LLMs, all these GPTs which you are using. All of them actually are based on this transformer architecture. So there are, I mean, more complicated versions of RNA. Is rather than having one single hidden unit, right? You can have multiple hidden units like this. So you take the input, you take multiple hidden inputs, and then process all of them together to get the output. And you repeat this. So these are called as deep recurrent neural networks. So in such cases, the hidden units could learn more specific information or something like that. Like one learns to attend to nouns or process them, like, or contains information of the subjects in the text. One characterizing verbs, adjectives, and so on, right? I mean, obviously they're not explicit, but just like how we humans process it, even they could like compartmentalize this information through different hidden units and leverage them. So we'll just go over a few questions here based on whatever we've discussed, and then I'll go through the code notebooks for this week. So here match the related applications of RNN from architectures in set A to applications in set B. So yeah, we saw those initial architectures, right? Many to many, many to one, all those. So among these three, uh, yeah, which one can be seen as many to one application? Which of this falls under the many to one category? Many meaning I have a sequence and I want to make one decision out of it or make an inference from it. Sentiment classification, right? Yeah. So this maps to sentiment classification. And what is many to many? Machine translation. Machine translation is like language translation kind of task. And one to many is music generation. That is like, yeah, if I give like genre as an input and getting a song out from a generative model. So what are the problems with traditional RNNs? So which of these apply, or all of the above, none of the above? All, right? Yeah. Mm, so we have this vanishing and exploding gradient problems because of long range inputs, problems in dealing with long run dependencies, processing the data sequentially. So the LSTM equations include the following terms. So this FT, IT, OT, CT, HT, right? So this HCT and HT are the cell state and hidden state. So the other three FT, IT, OT, these are like the weights, sigmoid outputs, right? So what are the functionalities of each gate? Uh, Forget gate. So which of these? So the three gates. Can you map which maps to forget gate here? A, B, or C? Forget gate decides how much of the old cell state should be kept, right? And what about input gate? B decides what new information should be stored in the cell state, correct? And then output gate controls the output to the next hidden state, right? So what are the key structural and gating mechanism differences between LSTMs and GRUs? So let's look at each of this element. Number of gates. So which of this is right of the four statements? LSTMs have 3 gates and GRUs have 2 gates. Right. The 3 gates which we just discussed, right? The input gate, forget gate. And what about how is memory handled in LSTMs and GRUs differently? B, right? Yeah. So LSTMs have separate memory cell by memory. I mean, it's saying cell state and hidden states are separate. So there are like two elements which get carried forward with time. GRUs combine both into a hidden state. Gating mechanisms. So yeah, which are the gate? Name the gates in LSTMs and GRUs. B. LSTMs have 3 gates: input, forget, and output. GRUs have only 2: update and reset gate. And which one is more complex, LSTMs or GRUs, and why? LSTM has more number of gates, so they are more complex. GRUs are less computationally expensive because they have fewer gates. So each gate is represented by a weight vector, right? So lesser gates means lesser weights I have. Uh, yeah, so which of the matrices here are responsible for vanishing or exploding gradients in RNN? So this is how the RNN function looks like. So there are different weights, right? There are like three matrices, this, and this. So which one is responsible for this problem in RNN? T minus 1. So UH, this vector, the matrix UH. So consider an RNN being trained on a sequence data using backpropagation through time. Now we have that matrix UH, right, which is responsible for forgetting and vanishing gradient. I mean vanishing gradients or exploding gradients. So if the eigenvalues of that is greater than 1, how can it possibly affect the training process? So if it is greater than 1 with when I'm back propagating, yeah, it is B. Because when I'm back propagating it through, I would be multiplying with this gradient, this matrix UH recurrently again and again, right? So in such cases, if the eigenvalue is greater than 1, I will keep amplifying the gradients. So I will end up facing this exploding gradient problem if the eigenvalue is greater than 1. Any questions or doubts still? So suppose so how does the an RNN look? It's something like this is how the hidden states get propagated, and then I have some inputs, and then I get some outputs, right? So let's say this is x1, x2, x3, and this will keep going on. And here I have h1, h2, h3, and this is my output y1, y2, y3. um, so say I have so I'm training this neural network like this RNN. So how what my loss, to train the loss I use, what is my loss function? It's usually a function of what my outputs are, right? So it goes from 1 to, let's just say these three elements as of now, and this is my set predictions, and then I have one real ground truth. So I have this loss computed at each of these elements, right? Here, say L1, L2, L3. So when I want to update a weight, so let's say this is my weight vector W here. So if I want to update W, so what would be the gradients like that will all contribute to this W? If I have to trace back the gradients, how would they flow? So this W is multiplied by, so I mean, so I'm doing wx1, wx2, wx3, all of this, right? And all of these are leading to my y1, y2, y3. So does y2 depend only on x2, or does it depend on any other inputs as well? In this, if this is how my graph looks like. Depends on previous one as well, right? Because this I mean it goes through this way and also like this, right? So my y2 is a function of both this hidden state h1 and x2, and this hidden state h1 is also contains information on x, so it has come through this, so it goes this way as well. And this x1 and x2, both of them affect y3. So if I have to update w, so one path which in which my gradient, so I have L1, right, which is like yeah, this, so this will affect it, and L2 will also affect it because it will affect it this way, because this it passes through x2, I mean w and x2. And there's also another path it will take a path like this also, because it's a function of x1 as well. So L from y3 also I'll have gradients. It'll go this way, it will pass like this, and the gradients will affect this way also. So with time it will affect my current input, I mean, yeah. So these weights, and then the one that process h, right, like that UH. So U and W, both of them, the gradients pass through this way. So yeah, this algorithm is called backpropagation through time because my gradients also get propagated to previous time inputs. But in CNNs, if I'm using a particular image, I do forward pass, backward pass, and I'm done. I'm not depending on my gradients don't get passed to my previous input. So right, so that's just backpropagation. This is called backpropagation through time. You can see my screen, right? The code notebook. Okay. So here we'll build a simple recurrent neural network that is trained to predict the next character, like which is what we do when we are typing, right? It predicts what our next character is. So if this is what I'm typing, like for an example, hey, how are you? So when I type HEY or HO and start typing HO, it should predict the next letter W, like the next element in my sequence. So this is something that predicts at a character level. So each character is encoded into an integer. Like, so this one here we are creating what are input sequence and this target sequences. That is, if my sequence is hey, how are you, where I've written just you, the target sequence is this. So when in a training, while training, so what trying to train is that if I write H, it should predict E. If I write E, it should predict Y. If right, it's like that. So if I write Y, it should predict O. If I write O, it should predict U, right? So this is what my input sequence would be, and this is my target sequence. So my loss is actually between what? If my input is H at current time step, I expect yt, if y1 is H, I mean if x1 is H, I expect y1 to be E. So that's why this is my input sequence and this is the target sequence. Does this make sense? Like anyone has any doubts? Here we are trying to predict character level sequence. I want you to understand the problem definition properly here. Now, okay, let me ask you a question here. So rather than predicting a character, suppose I'm operating at a word level. That is, I have a dictionary of words. So in that case, how would this how differently would I prepare the data? What would my input sequence data be and target sequence data be for the same examples? Hey, how are you? Good, I'm fine. Have a nice day. These three. Uh, Instead of character level prediction, if I have to do word level prediction, how would I prepare the data? Can you give me an example of that first input sequence? Can any of you tell? You have to translate the same logic to words, whatever I explained for characters. Any word can be missing instead of a character. It's not any word, right? If my task is to predict the next word, it has to be that. So, like that, it would be my input sequence would be hey, how are, and target would be how are you, because I want to map here to how, right? Like how should be mapped to r, prediction r, and r should be mapped to prediction u. So this is how my data would be prepared as. So here what we've done is we've padded all the strings to be of same size, that is, so they are padded to make them as 15 characters by appending just like an empty string. So what is the shape of my input? It is 3 because I have 3 sentences, right? 3 sentences. So it is padded to the whole length of 15. That means I'm predicting next character, right? So I have 14, the size of my input would be 14 elements, so that I train to predict the next 14 elements, the next 14 characters for each of them. And so here we are seeing that the one hot encoding size for this is 17. So why is this 17? In this example, why is it 17? Suppose if I change my examples, would this change? For spaces, no. So let's see. So it is 17 because of the unique elements in these sequences. So here we've created a dictionary, right? Like what all letters are present in these 3 statements. So there are total of yeah, so there are 17 different characters here. Yeah, I mean even space is one character, but there are 17 different characters. So if I elaborate this to more examples, say 10 or more examples, then what would you expect this dictionary length to be? It would include, yeah, it would end up including um, all the alphabets, right? So because we have taken this very few examples here, I mean few statements here, we're getting 17. So anyway, so the one hot encoding basically refers to the choice of predictions we have, right? So for this data set, I have 17 choices. I need to predict one of them. In general, I would have 27. One for space there. So that's why this is how my input is. Um, that explains my input shape. And yeah, why have I done this one hot encoding only to the input, and for the target I'm not really doing it, right? I'm just directly using it. Why so? So why am I preserving, I mean using, keeping the target as is, but only input I'm doing the one hot encoding? Order matters after prediction. I didn't really get you. So for my when I'm designing the LSTM, I mean not LSTM, like the RNN, that last layer, to give out my prediction YT, I will obviously use some weights, right? Weights, and then followed by a softmax layer or something. So that last layer, I will ensure that it will give out a dimension of 17, and then I do softmax over it to pick one of them. So I would do using some, I mean, like, so now the task becomes like classification task. So these become my labels. These become my labels, right? Like, so that the number of classes I have is 17 classes. So 17 classes, I process my input, and I want to predict one of the 17 classes. So here you're defining a simple recurrent neural network, yeah, using just the torch layer RNN. But what are the parameters that you need to define? That is your input size, hidden dimension, and the number of layers you want. Number of layers, and then the fully connected layer. This is my decision layer, which I just said, right? So output size would be 17, which we pass here. So I give out, like, take my hidden dimension, and then I want to predict one of the 17 characters. So if I whenever I'm passing an input, yeah, for the first input, as in, so I have to start from some h naught, right? Because I don't have h naught is something that is propagated. But initially I need something. So that is why we have this initializing a hidden state, which gives me a zeros, which is of the required dimension. Batch size, number of layers, hidden dimension, you generate. So it basically takes in a zero input as like h naught, and I pass in my whole sequence. So this is my input sequence. and the input. Uh, so this is x consisting of all x1 x2 to xt and one hidden state which is h naught, and output, this is the prediction which I am giving and the hidden state. So once I get my hidden states as output, I pass all of them through the fully connected layer, which is this layer, to give out my predictions, which is one of the 17 classes. Any doubts on how this RNN is defined here? Okay. So fine, now this is how it as we define a simple RNN model. Now we instantiate that model. Uh, yeah, my input size is dictionary size. It's 17 because I have one hot encoded them into a 17 dimensional vector, right? So it's a 17 dimensional vector. Output size is also a 17 dimensional vector, and hidden dimension, this could be anything you can define on your own, and number of layers is one, a single recurrent neural net. I'm not really defining any deep neural network here. And the criterion here is cross entropy loss. Just I'm trying to uh, it's just like classification, right? Classifying it into one of the characters, predicting the next character. And I define an optimizer and to optimize the model parameters. So this is my training loop where I have the input sequence, I have the optimizer, right? So at every step, I clear the gradient from my previous step, pass the input through the model, I get my output and hidden state. Then I have my target, so I have this cross entropy loss between the output and target sequence. Then I backward pass through it, do the back propagation, update the parameters, and do the training. So here this is the prediction function, that is so when I'm predicting, how do I do the prediction? Do I give the whole, like, hey, how are you, yo, and will it give me the whole sequence, or do I have to do it element by element? What do you think? So training time, my input sequence is this, right? Hey, how are, yeah, or rather, because we're dealing with characters, training time, my input sequence is this. But when testing, what would my input sequence be? I will start with a H, that's all, just single character, and I expect it to predict E, and then I expect it to predict Y, and so on, right? So I have the character, and I get its mapping, the dictionary, with based on my dictionary. I do one hot encoding for it, and then I pass that character through the model, get my output and prediction, and apply softmax over it to identify what it predicts as the next character. So this is how I'm doing, but yeah. So I start with an initial character. I pass it through the model. I get a new character. I append it to my initial character. So first when I pass H, that's the initial character H. It would predict E, suppose. So now I append E to H, and then I pa- I keep doing this in loop. Let's print this and see, right? So here I'm starting with this word good. So if I give good, then it predicted a space after that in the first pass. Then it predicted I, and then it predicted another space. Then it predicted A. So what is it doing with time? It has predicted good, I am fine. So I said here, and it predicted with time, character by character, it predicted, hey, how are you? So, like as I asked, if I have to change this thing from character to word, the change I'll have to do, like the logic remains the exact same thing. So, as instead of this, uh, I mean dictionary which I've created for character, like having character to integer mapping, I'll have word to integer mapping, and then do the exact same thing. But all this will work fine for a simple, like if I have just a few words here, it can just do good only here, right? It can't really generalize to real text and so on. So in such cases there is something called tokenizers, which basically forms this dictionary. So you take all your text, and that tokenizer is probably create like a dictionary of the whole words present, I mean the whole Oxford dictionary, suppose. So it will map it into a vectorized form, and once it does that, the logic remains the same. Like when you're scaling these models to huge data, huge models, that's what is done usually. How it knows when to stop predicting? Yeah, that's a very good question. So in this case here, it's actually hard coded. It's hard coded here to predict 15 characters. Right, so based on, so how many times I want to keep calling the model, based on that, this is what happens. But in general, when we are training it on lots of data, what is done is there is something called start of token, end of token, end of statement, start of statement. It's usually called as start of statement and end of statement. So you usually start with, like, my input would be, um, so input would be something like this. I would give start of statement and how. So I will give this, and I will expect it to predict, are you, I expect it to predict, yeah. So my input would be start of sentence and the text how. Then I expect it to put, expected would be, are you one by one, obviously I'm saying element by element, and at if it thinks it is done, then it will actually predict this end of statement. So if it the model knows when to end, that means it has predicted out the token end of statement. That is when you stop. If you get an end of statement, then you stop calling the loop. So this hard coding of 10 15 is not done in general. So you keep checking until it is not predicted. You will have that while it has not predicted end of statement, you keep doing it to predict the next word. So that is how it is done in general. uh, does that explain your question? So I'll go through the LSTM notebook as well. Yeah, this is, I think, some time series data here. So yeah, this is anyway in numbers form, so there is no issue of encoding them and using a dictionary and numbers as such. This directly act as inputs. But yeah. Yeah, here as well, I mean, this GRU and LSTMnet, it is pretty much the same thing what we did earlier. Then you know, define the input dimension, output dimension, hidden dimension, number of layers, so on, and use the GRU element like from the torch neural network here, and we have a fully connected layer to predict the output. Oh, by the way, in that previous case, we used a softmax function, right? But here we parsing. Uh, so yeah, a general question. How do you decide which function would you want to use for activation, like sigmoid when or ReLU when, and so on? Like, why was the choice sigmoid in the GRU units, like the cells? I mean the gates, but not ReLU. If I have to do a classification task, what would my choice be? If I have to do a regression task, what would my choice be for the activation function on my final layer output? Range of numbers like 0 to 1 or -1 to 1. Yeah, if I want my number. Yeah, so so here we define like this is a training loop where I'm defining what model I want to use, either GRU or LSTMnet. Uh, so here the output dimension is 1. It is like a regression, right? I'm not picking what value, like letter. I don't have a choice. It's a real number here. So that's why the output dimension is 1, and I'm not going to use softmax here. So it will be like an MSE loss because I'm regressing towards a real value. Like I want to predict the exact value, right? So I'll use a mean square error loss. So that's why the criterion is defined as MSE loss, and the output dimension is 1. I want to predict a single number. And this is my optimizer. I'm putting it in train mode. I iterate over it. So similar to how we did last time, initialize the hidden layer, like the zeros of it. Then in the train loader, so this model.0grad will get rid of the previous gradients. So I pass the current input to the model, get my output hidden state, and pass it, do compute the mean square error loss, do backward prop through it, and update the weights. So all this is to just record what is happening. Yeah. And yeah, this is the evaluation function. So these are like the different test sequences given and what the model is predicted, I think. So you give this element and yeah, the actual one is the blue curve and the green dots is what is getting predicted with time what it is predicted. So any doubts on this? This is not very detailed like the previous ones because you directly use the LSTM network right here. So it's pretty straightforward only. You have access to this notebooks, right? You can play around with it yourself. Okay, then like that's all I have. It's taking some time to train. You can check it out yourself. How are you finding the course? Like the assignments and tests. Okay. You are able to follow what I'm explaining, right? I hope. If you have any feedback, you can let me know. I think for this week it pretty much covers most basic stuff, fundamentals of all computer vision. From the next week it starts with this attention models and generative models, which are more trending new topics for current world. Okay, I'll stop this. It is doing the GRE model. We can see the GRE outputs at least. Do we still use these old topics? Yeah, I mean, the newer ones are very much like tweaks and all to make get things working, but fundamentally, what is happening is still what is taught till now only, I think, right? Uh, if you have to understand why attention came up and all this, you should still know how things evolved. So that trajectory always gives a very good perspective, I think. Although you don't use it in current times, uh, like you can always, you might encounter some issues which kind of mimics what had happened once upon a time and how did people address it. So in some different context, if you still come up with same issues, you can use such fixes. So even if they are old, I think those basics are still very very important and relevant to understand. Even this CNNs, like nowadays, no one really uses those standard ResNet architectures. Everyone uses vision transformers because they work well and all that thing. But still, yeah, the ideas are still revisited here and there once in a while. So that understanding that progression is a very good thing and important, I think, because you'll always be questioned the basics. So yeah. Okay then, if there are no more questions, we can end the session here.